Hi. So what we saw last time was that if we had a theory so if you have a set of theory or a set of axioms, T, extending our basic set Q here, and we said if T was recursively axiomatizable. So this could mean that there is an algorithm for deciding what the members of T are, what the axioms of T are. So being recursively axiomatized, well, let's see, this was given to us on definition 637. So recursively axiomatizable says just a little bit more than saying that the axioms of T are given to us in some algorithmic way. It says, actually, if I look at all of the consequences of T, there's an algorithm that gives me those, right? This means here, this set here, the set here, this set here can be given as or equals where this is a recursively given set of axioms. So you say the theory is recursively axiomatizable, means there is some T0, possibly a subset of T, right? Such that the consequences of this T0 are the consequences of T. And T0 is given by an algorithm. So there's a recursive function that will return 1 or 0, depending on whether the input was a Gödel number of something from T or not. Recursive set of axioms. And what we saw was that if you've got a recursively axiomatizable theory, one can check whether something is a proof from those axioms. Right? One can check whether n is a code number for proof from those axioms. Or you could give me the code number of some sigma and say, does n code a proof from T of that sigma? And each of those are algorithmic processes. Right? So it's an algorithmic process to check, so A, if n is a code of a proof, or B is a two-place relation, if n is a code of a proof of of sigma in T. So whether T can prove sigma or not. So given a number n, we can check if it's a bona fide code of a proof. You give me an n and a sigma, and I can check whether n codes proof whose last line is sigma. So these can be given to us by recursive functions. So the sum here. So in case A, I can say there is this recursive function which will give me a 1 or 0 if n is a code of a proof and B, and for B, I put a little 0 down here, T for n. And K, again, is 1 and 0. If n codes proof in T, sigma, and the Gödel number of sigma is K. And I emphasize that saying you can check proofs is not the same as providing proofs. You can set a program running that'll just start checking different numbers. N is 1, n equals 2, n equals 3, and so on. And then it'll can print out the last line of those n's that code proofs. So it can produce theorems like this. But if you ask me whether a certain sigma is a theorem or not, all I can do is just let this machine run and hope that sigma comes up. On the other hand, if T is complete, meaning the set of its consequences, either sigma or not sigma is in there, then I do know that eventually this process will produce me an answer. It'll either come across sigma or not sigma. So in the case that T is complete and recursively axiomatizable, so we do have an algorithm for checking theoremhood. We run the machine that checks different numbers and looks for their last lines. And because we're assuming it's complete, we know T either proves sigma or not sigma, so one of these two will occur. We don't know when necessarily, but we know that it will happen. Okay, so what we're going to show today is the Gödel first incompleteness theorem. And this will show, in fact, that if I've got a theory that extends Q and it's recursively axiomatizable, then actually it can't be complete. And in particular, this will show that the truths of arithmetic are not recursively axiomatizable. Okay, so that's what we'll do now. Okay, so this is the Gödel first incompleteness theorem here. And it says there is no T extending the 7 axioms of Q such that T is consistent, recursively axiomatizable, and complete. So, of course, we're interested in consistent sets of axioms. Inconsistent set of axioms are of no interest to us. And recursively axiomatizable, we've just discussed here. And complete would be useful because then we would know that anything is either provable or disprovable from T. And this was part of David Hilbert's aim, was to find some kind of complete axiomatization for mathematics, or in particular for arithmetic. Okay, so let's suppose for a contradiction there is such a T. Now, theorem 627 said every recursive function is representable in Q. So in a sense, this is the analogy for saying something is definable in a structure. A theory can prove basic facts about the graph of the function, if you look back at that definition. So if I've got a function from n or n squared or whatever to n, if it's recursive, there's a formula. Let's say rho, which tells me about f. So that if f of n equals m, Q can prove that formula about those number terms, right? N and m. In fact, it turns out, a theorem we didn't prove, but I just asserted is, the functions that are representable in Q are precisely the recursive functions. This is the utility of Q. Well, if I can prove something in Q, I can certainly prove it in a larger theory. I only needed axioms from Q to do this. So clearly also T proves. The same thing. Now, as rho f represents the function, if f of n is different from m, then also we have that Q, and so T, rho, after all, is defining for us in T the graph of the function. So if f of n is not m, we can prove that T proves not rho. So in this sense, rho f defines the function f in Q, or indeed T. Right. Could I read out the last line? This one here? So I didn't see it immediately. Well, I'll read out from here. Clearly also, T proves, and this is rho sub f, boldface n, boldface m. As rho f represents f, if f of n is different from m, then also T proves not rho f n m. So this is what we mean by saying rho f defines the function f in Qt. I mean, this is just me being a bit colloquial here. The official terminology is about representability. Okay. Now we're assuming that there is a T that's consistent, recursively axiomatizable, and complete. So the last theorem that I was writing up on the board, this says, in fact, then there is an algorithm for checking of any particular code number of a formula, Gödel number of a formula, whether it's provable from T or not. It's completeness that allows us to do it. We run that search program, and we just wait until either sigma or not sigma pops out. It gets printed. So lemma 641 said that the set of consequences then of T is actually recursive. Since T is recursively axiomatizable and complete. We're assuming for a contradiction, right, that the set of, okay, Gödel numbers of sigma such that T proves sigma here, this is a recursive set. So the characteristic function of this set of numbers is a recursive function. So there's a recursive function, well, rather a lot of f's around. Let's call it f still in, to stick with the notes. So to spell this out, f of m is 1 or 0 if there's sigma such that the Gödel number of sigma equals m and T proves sigma. And it's 0 otherwise. So now I think of the formula, because f is a recursive function, there's a formula rho sub f that defines this f here in the theory T. Hence above, there's a formula rho sub f, right, of two free variables that defines f. Okay, so in other words, if f of m equals I, then T proves rho f m I. And here I is 0 or 1. And if it's not I, then T proves not rho F M I here. But now from this row, we can get a formula that defines a set of theorems of T. And then we're close to our contradiction. So let's look at the formula theta of x, right? Just rho x and 1 here. This defines in T the set of theorems of T. So what does this mean? So we're saying if T proves phi, right, this means f of the Gödel number of phi here is 1, right? Because what was f? F returned a 1 if T proved phi, right? Returned a 1 for the Gödel number of this theorem. Yeah. But this then says, okay, if rho f represents f, T rho f, Gödel number of phi here is 1. But that is what theta is. So this is just equivalent to saying T proves theta of the Gödel number of phi. So let me write this as like here. Okay, hope that's enough for the last page. Yeah. So if T proves phi, then I've got that this implies T proves theta of the Gödel number of phi. If T does not prove phi, then we're in the if not over here. T does not prove phi. So f of the Gödel number of phi should be 0. So this is going to be that T proves not rho f of Gödel number of numeral for the Gödel number of phi, numeral for number 1 here. And this proves, but this is just theta, right? Theta is just abbreviating this. row fx1. So now what have I got? I've got here this formula theta, right? That's defining in the theory T Gödel numbers of the theorems of T. And this contradicts an earlier lemma, 635. Okay. The theta defines in T the set of theorems of T. This contradicts 635. So our conclusion then is, right, one of these has to fail, right? We can't have a T that is both consistent, recursively axiomatizable, and complete. Right? So if T is consistent, recursively axiomatizable, it's incomplete. So there are some comments to make. Well, there are many comments to make, and many people have commented. Q is a very weak theory, with just these 7 axioms in, and we didn't discuss it, but there's a number of basic arithmetical facts that Q can't prove. It can prove lots of things, but there are things that it can't prove. But actually, the weaker the theory we have here, the stronger this theorem becomes, because it's about all possible extensions of this theory. So we make this as weak as possible, and then we maximize all possible extensions. So the weaker Q is, the stronger this theorem is. It's talking about all possible T's that extend Q. So, well, I'll discuss it a little bit more in a moment. Let's just draw out this final corollary. So, true arithmetic is the theory of the natural number structure. It's the collection of everything that's true in the natural numbers. So this is what number theorists are striving for, to find the truths in the natural number structure, Q. So it's not recursively axiomatizable. And the proof of this here is it's being the set of things true in a structure means, first of all, it's consistent. Nothing is true and false in a structure. It's also complete because everything in E sigma is either true or false in the structure. In other words, either sigma or not sigma is in here for every sigma in the language for arithmetic. So this is both consistent and complete. All the axioms of Q are true in the natural number structure. So by the theorem, right, it's incomplete. Sorry, by the theorem, it's not recursively axiomatizable. So by the first incompleteness theorem, it is not recursively axiomatizable. Okay, so the comment immediately above the corollary here is, I said, well, this is one of the most significant theorems in logic, right? Certainly in the mid-20th century, this was not what was expected. David Hilbert and his co-workers had thought that we just needed to find the right collection of axioms, and we would be able to then deduce all the truths of arithmetic from those axioms, right? In theory, at least. Right? So what we found then, though, is that what Gödel showed is upset that apple cart completely. He showed that this so-called Hilbert programs are doomed to failure, that there was no way we could find a sensibly given. I mean, he talked about systems of axioms extending those of Russell and Whitehead's Principia Mathematica, because he didn't have the the nomenclature or the concepts of something being kind of algorithmically given by recursive or computable functions. Right? But he realized that if you had, any sufficiently strong theory, if that theory was given to you in some kind of effective way, right, it was not going to be able to prove all of the axioms. Sorry, it wasn't going to be able to prove, well, first of all the truths of arithmetic, right? But also that there was no way that it could actually define within the theory those Gödel numbers of theorems, statements that would be theorems. Right? So this was kind of a shock. Of course, this was kind of a shock to Hilbert and his score. Right? This was not what was predicted. And many people since have written extensively about the Gödel incompleteness theorems, and not all to great sense. I mean, I think acre feet of ink have been expended on writing about the first incompleteness theorem. Probably more has been published about this theorem than, well, probably any other theorem. I mean, in mathematics, because not actually only mathematicians write about it. People from all walks of life have, rightly or wrongly, tried to adduce various things about their own theories because of the Gödel incompleteness theorem. So the paraphrase in that last corollary is somehow, not all truths are provable. I mean, this is rather a loose statement, but it kind of captures in a way, if you say specifically what it means that, all the true statements of arithmetic are not provable from any given recursive set of axioms. What it doesn't say is that you can't talk about a stronger set of axioms, and then maybe you can prove some more things. This is not at all ruled out by Gödel. Just because you can't prove something in a certain axiom system may just simply mean your axiom system isn't strong enough to decide yes or no about the particular statement you're interested in. So to say that all truths are not all truths are provable is really a misstatement, right? It's not to take the spirit of the incompleteness theorem correctly. It's given an axiom system, not all truths are provable in that system. It doesn't say that there aren't stronger systems in which something could be provable. So what the theorem is saying then is that if you've got a recursively axiomatizable set, which is consistent, then it's going to be incomplete. So there are going to be unprovable statements. There are going to be sentences sigma such that neither sigma nor not sigma is provable from your axioms, although one of sigma or not sigma is going to be true in the natural numbers. So the Gödel theorem isn't also just about number systems. It talks about any theory that extends Q. So this would include theories that include analysis, say, which have a lot more complicated axiomatizations than axiomatizations for number theory. Right? It includes set theory, right, in which we can kind of provide a foundations for all of mathematics. So if we write down a set of axioms for set theory, which is commonly called ZF or Zermelo-Frankel for these set of axioms, there are going to be things that that set of axioms, ZF, can prove, cannot prove, or disprove. So that's the state of things after the first incompleteness theorem. So I'll just finish by talking a little bit about the second incompleteness theorem. Right? So Gödel then realized actually that from the first incompleteness theorem, you could look at for a very specific statement that was not provable or disprovable. And that specific statement was actually something that's about the consistency of the theory itself. So we'll call this statement con for consistency, con t. We'll look and see what con t is in a moment. So Gödel realized that from a theory T, if it was consistent, recursively axiomatizable, there was a statement that expressed the consistency of T within the language of number theory, such that T did not prove or disprove con T. So it's a very concrete example of something that was neither provable nor disprovable. So let's just see what that was. Right? So this is just the last page of the notes, page 104. So this is the Gödel second incompleteness theorem over here. So we saw in the first incompleteness theorem that if T extended Q and was recursively axiomatizable and consistent, too many words beginning with C, yeah? Then there'd be sigma in the language, right here, such that T did not prove sigma and T did not prove not sigma, right? It's incomplete, right? Now, as I've said on the board at the beginning of the talk, right, we've got this relation here that says that Y is the prime power code of a proof of some sentence sigma or some formula sigma, and the Gödel number of sigmas n. Of a proof in the algorithmically given T of the formula phi, and the Gödel number of phi is n. Here. Okay, so this is something that's decidable. It's a recursive predicate of y and n here. And we saw we could take the characteristic function of this and we'd find a recursive function here. So this is then definable in T. Right? So that is, there's a formula, and in the notes I've called this pi. So again, in the language, so that if I've got this relationship holds, then in T I can prove pi of y and n. And if this doesn't hold, maybe y doesn't code a proof, or it's not a proof of n, then T proves not pi of these number terms here. Now, if a theory is inconsistent, it can prove a contradiction. It can prove some sentence Tor and not Tor. Or since we're talking about number theory, we can just choose our favorite contradiction. 2 plus 2 is not 4, or 0 is the same as 1. So let's take 0 equals 1 as our favorite contradiction. Now, an inconsistent theory can prove anything. So an inconsistent theory can prove 0 equals 1, but a consistent theory can't. So one way I can write down a sentence in our language which says, in effect, that our theory is consistent, is to say there is no proof y of naught equals 1. So let's call it con t. So we could take this as saying it's not the case that there is a number y that gives us a proof in T of, well, naught equals 1. Here. So So we take this as kind of, sometimes this is called the formal consistency statement. Con T here says theory T is consistent. There's no code number of a proof of this contradiction, naught equals 1, down here. And Gödel realized after he'd proved the first incompleteness theorem that there was this second incompleteness theorem here. Suppose T, and now we have to have a little bit more than Q. We have to have that T extends the axioms of Peano arithmetic. Some induction is needed for this theorem, which isn't available in Q. Q has no axioms about induction. And we suppose T is, again, consistent and recursively axiomatizable. Then the conclusion is, from T, it can't prove con T. If it's consistent, it can't prove not con T. Because not con T will be saying there is a proof of naught equals 1. Right? So being consistent, we see that it doesn't prove not con T. So the substance of the theorem is saying that it doesn't prove con T here. Okay, so this then is a very concrete example of a statement that is not provable nor disprovable, right, in T. It's the consistency statement of T itself. So this, I think, is a remarkable extension of the first theorem. Right? So it says, again, any formal theory, as long as it extends the axioms of PA, right, can't prove its own consistency. Now, again, you want to make sure that this is quoted right. It doesn't mean that you can't go from a theory T to a larger theory T prime. And in the larger theory T prime, you might be able to prove the consistency of T. And that's indeed what happens. In set theory, in ZF, this is a stronger set of axioms than PA. In ZF, we can prove the consistency of PA, of number theory. And in things stronger than just ordinary set theory, we can prove the consistency of ZF. So it doesn't mean that we have, we're suddenly thrown into, doubts and despairs about number theory. Right? It just means within number theory itself, we can't prove the consistency of number theory. We have to go to a stronger system in order to do that. So finally, just then, so an anecdote about this. So when Gödel presented his remarks at a conference in Königsberg about the first incompleteness theorem, it appears that people didn't really understand. It's not clear that anybody in the room, other than von Neumann, actually understood what Gödel had said. I mean, he said it in rather few remarks just at the end of a kind of a roundtable discussion about consistency of theories in Hilbert's program. And he sort of piped up and said, well, actually, I can prove blah, 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 the first incompleteness theorem, and gave some ideas about that. But from discussions of people afterwards, it wasn't clear that anybody kind of really taken this on board, except for von Neumann, who immediately realized the import of Gödel's remarks for Hilbert's program. So von Neumann went away and thought about this for a while, and he realized that what you could do is just formalize the proof of the first incompleteness theorem, and you would end up with the second incompleteness theorem. That's how you do it, actually. You look at the proof of the first incompleteness theorem, and you do that, or you formalize that, and you think about that within the axiomatic framework T. So he then wrote to Gödel saying that, oh, look, he could do this kind of fancy new argument. He could actually prove the second incompleteness theorem, right? And Gödel wrote back and said, yes, I know. I've already submitted an abstract of the paper to the journal. So Gödel had pipped von Neumann to the post there, and whether this is a coincidence or not, but then von Neumann, he kind of left mathematical logic at this point and worked in other areas of mathematics and never went back to axiomatics. So that was kind of the final point of the story for von Neumann. But logicians today sort of study the incompleteness theorems in great detail, and you can pick up many a textbook which are just devoted to studies of incompleteness phenomena in different guises.